Hi, in this video we're going to continue our discussion of section 12.4, all about the cross product. So the idea of the cross product is that given two vectors, A, which is going to be A1, A2, A3, should already start ringing bells if you watched the last video, and B, B1, B2, B3, we want a vector that is perpendicular or orthogonal to both A and B. So the idea is that we have a picture like A is going off in this direction, B is going off in this direction, and in 2D land that was only possible. That is it for being perpendicular. But in 3D land, we hopefully know there's a third way to go here. And this would be like A cross B. Yeah. I mean, the way I'm visualizing it, it works, but it all depends on the visual here. So we want to get out of the plane. That's going to be really important. That's why this section is important before we talk about planes in section 12.5. So we're trying to get out of the plane that's generated by A and B. Two vectors together make a plane. We want to see like what would be the vector pointing orthogonal to both of them, or orthogonal to the plane. So the definition that we will use is that A cross B will be the determinant of the following 3x3 matrix. We're going to put I, J, K in the first row, the components of A in the second row, and the components of B in the third row. And we're going to do the determinant of this 3x3. Notice it's not exactly a standard determinant anymore. We snuck I, J, and K into the top row, but this works for most students. So again, this is the determinant with two ends. And what you would notice if you follow the technique we used in the last video, I'm just going to move that I around. So it'll be A2, A3, B2, B3 in the I direction. So that's the one associated with this, highlighting, that minor, minus the second minor, A1, A3, B1, B3 in the J component, plus, so sorry, really quick, that J1's like this. I hope you can see that. Plus A1, A2, and I'm squeezing things in, I'm sorry, B1, B2 in the K component, which would look like that. And that's how we would define the cross product. I'm not going to write out the other formula we'd get because, again, it would look really tedious and just kind of confusing, to be honest. But we're going to notice a few things about this. One, this cross product is giving me a vector. Notice it has I, J, K components. This is not the same as a dot product, which was not a vector anymore. When I did the dot product, I got a scalar. We would say that scalar had something to do with the angle. This cross product is giving me a vector. And what's special about the vector? One more time, A cross B is orthogonal or perpendicular to both A and B, both of them. And 3, A cross B is not the same as B cross A. They're opposites. Okay, so specifically, what I want you to remember from this is that they are not commutative. The order you do this matters, but they are parallel. A cross B is parallel to B cross A because they have the same magnitude, they're just opposite signs. Let's talk about how I knew which way my cross product would output. The cross product follows the right-hand rule. That's how I was able to know how my cross product should look. Graphically, that's if A is going this way. I'm changing it from what I drew in the last picture. And B is going this way in like the J direction, so to speak. Then their cross product has to go up. This is the right hand rule because if I draw up my hand, my right hand, and my vector A pointed out that way, and vector B was shooting out the palm of your right hand, then vector A cross B is shooting out of your thumb. Okay? It's the right hand, not the left hand. B is coming out of the palm. That's what makes it the right hand rule. You could also picture twisting your fingers from A to B using your right hand. If you twist your fingers, you're going to have your thumb pointing up in the direction of A cross B. Very mildly important. It helps you spatially orient. Then that would be good. Example really quick. If I have a vector U, 3i plus j minus 2k, and a vector V, I plus j plus k, the question might say find two vectors orthogonal to both U and V. The idea here, when you see orthogonal to both, that should scream at you by the end of this course, oh, I better do the cross product. So what does that look like? I'm going to make an I column, a j column, and a k column. You don't have to have this much space, but this is how I'm organizing my work. I'm going to put U in the second row. The first vector goes in the second row. I know that might sound confusing at first, but it's because the first row always will have I, j, and k in it. Notice how I put the I component in the I column, the j component in the j column, the k component in the k column. Notice how I kept track of the signs and the coefficients. And then this last row is 1, 1, 1 because those are the components of the v vector. So what do we have here? We have, sometimes I write it like this. You might see me do this. I'm just going to get you acclimated to both things. I times this situation minus j times this minor plus k times the last. I'll use the highlighting one more time here in case that was really helping you. For the I, that's first row, first column. Notice the minor matrix. For the j, that's second column, first row. Notice the minor matrix. Notice what j is multiplying with. For the k, that's first row, third column. Notice the minor matrix that I got from crossing those two rows and that row and that column out. So now we would finish this up. 1 plus 2. I know sometimes I have had some students get really confused here. If you're still feeling lost with cross products here, try to do some determinants, get acclimated, see if you can get the rest of the pieces in order here. Minus -3 plus 2 j hat plus -3 minus 1 k hat, or 3i plus j minus 4k. That's one vector, and and use the opposite. -3i minus j plus 4k. Because these are parallel, you could use any scalar multiple, but this is my 1, 2 vector. One vector that's orthogonal to both u and v, the second vector orthogonal to both u and v. Okay? Find a unit vector orthogonal to both a, -1, 1, -1, and b, 0, 3, 4. Can you do this? You should feel confident that you can do this. Here's some hints. You can pause the video if you want to try it, if you feel like you have a good idea. The hint would be, for any time they say a unit vector, if someone's asking about a unit vector, first find the vector and then divide by the length. So we're going to first find the vector that's orthogonal to both of them. You should feel really confident that you know how to do that. You're going to do A cross B. Could you do B cross A? Yes, B cross A would just be fine. But we usually will use the order that's, kind of suggested by the problem. So again, I'm going to have an I column, a J column, and a K column every single time you do the cross product. You should have I, J, K in the first row. Put A's components in the second row, B's components in the third row. Bingo, bango, bongo. And we're going to go for it. We're going to have, right now I want you to pause and really try it. If you weren't able to write down that determinant, try writing the minors out. Try and see it. Actually write something down on your paper, see if you get any mistakes. 3, 2, 1. So I'd have 1, -1, 3, 4 with I minus -1, -1, 0, 4 with J plus -1, 1, 0, 3 with our guy K. Did you get that right? Did you make mistakes? Literally try covering up that part of the screen with that column, with that row. Simplifying this, I get 4 plus 3 in the I component minus -4 is 0 in the J component plus -3 minus 0 in the K component. So I think I'm going to get 7I plus 4J minus 3K. Are we done? No. That's not a unit vector. It's very unlikely to be a unit vector with that big of numbers, with that big of components. So now we're going to normalize or divide by the length or the magnitude of A cross B. It'll be 49 plus 16 plus 9 74 So a nice unit vector here would be 1 over root 74, 7i plus 4j minus 3k. And I know one thing that students get hung up on here is, well, if it starts off in component notation, do I have to leave it in component notation? No, absolutely not. You should feel free to leave it in IJK notation. That's literally what I would do. One other formula that we're not going to develop, but is useful for us. If you know the angle between A and B, so one more time, I guess I've been drawing them with a kind of orthogonal. That doesn't look too orthogonal, I hope. There's A, there's B. We know A cross B is still going to be sticking up and out. But if you know this angle, the angle theta, then A cross B, the magnitude of A cross B is equal to the magnitude of A times the magnitude of B, sorry, don't use dot, we don't use dot, times sine theta. And this can be a really helpful formula for a few applications that we'll see in the next video. But right now, since that relationship is true, so if theta equals 0 or pi, sine of theta equals 0. So that would mean the magnitude of A cross B would be A times B, the length of A times the length of B, times 0, which would be 0. And as we've learned, or as I think I've discussed in one of these videos, this means A cross B is the 0 vector. There's only one vector with the magnitude of 0, and that's a 0 vector. So what? So what? What would that possibly mean? It means that, so, therefore, let's just say therefore, if A cross B equals 0, then A and B are parallel. It means that A and B, the angle must have been 0 or pi, which is exactly what we talked about being parallel in the last video. Realistically, it's still easiest to check for scalar multiples. Would you rather check if two vectors are scalar multiples, or would you rather do that whole cross product process? It's almost certainly easier to check if they're scalar multiples. Usually that's something you can do relatively by sight. But we are going to use this theorem, this formula, throughout the course. It's just something helpful to know. If the cross product didn't work out, if the last vector was not found, was a 0 vector, it meant that there weren't enough information to get out of that plane that A and B are on, because those two vectors are parallel, so there's just one direction being talked about. I'll say that again. If A and B are parallel, like they're both going in the same direction, or they're both going in opposite directions, there's too many vectors I could be. I could go up, I could go out, I could go down, right? There's a whole direction I could be. So it's not easy to talk about cross product anymore. There's only one direction. I'll point out that's a really good picture, except I didn't label A and B correctly. So if we had A one way and B the other way, Those are all the different options for the cross product. That's why the cross product isn't doing what we want. That's why the cross product would be 0. We don't know which one of these out directions could we go. I could even do extra ones and make the picture look uglier. Right? There's just so many out of the plane we could get. All right, so that's enough for this video. Watch the next one to see how we can apply the cross product to get us a few interesting things from physics and math/geometry. Thanks for watching this one. See you next time. Bye.